Hello, and welcome to problem set 138. Today, we are going to continue our discussion on series. The most important part here is to remember that with all of these tests, we're really trying to see the fruit of these series. What's going to come out of these things? What is the result of adding up all of these things over an infinite amount? It's like our lifetime, right? You're adding up infinite moments, an infinite number of moments over your whole life, and to say, where are we going to end up? What kind of fruit is this life showing? Today, uh, we are studying the alternating series test or Leibniz theorem. So, Leibniz, who's a good guy, right? So, he's there. He's one of the fathers of calculus, right? You've got Newton, you've got Leibniz, you've got all these guys who are trying to set up calculus. And Leibniz, as he's studying this, says, well, I'm not satisfied with absolute convergence. So a series that has positive, negative, positive, negative, positive, negative. Our absolute convergence, we said, was you take the absolute value and work with that function. Okay. So if the absolute value converges, then most likely your alternating series, where it's positive, negative, will also converge. Here, the alternating series test or Leibniz theorem says this. If we have a series that looks like this, so basically we have a series that alternates positive and negative terms, and then we have some quantity that we're adding over and over and over again. So if we have this, and if the following conditions are true, which is an is always greater than a to the n minus n plus 1, or equal. So at infinity, as we get bigger and bigger and bigger, an has to be greater than the next term. So basically, are terms getting smaller for any n that I choose? And is the limit as n approaches infinity of an equal to 0? So are terms getting smaller every time, no matter what? This part, not the negative positive part, but this part. And is the limit going to 0? If this is true, then we can apply Leibniz theorem and say that this series converges conditionally. Okay? So we can say that that series converges conditionally. Now, how do we do this? Well, we actually have to jump through. Conditional convergence is a little bit softer, a little bit lighter than absolute convergence. So we would rather say this series converges absolutely. The absolute value of it will converge. So this series converges absolutely. This is like a lighter convergence. Like it still converges, but it's not as powerful. And so I would rather say that it converges absolutely. And if it doesn't, then I'm willing to settle for converging conditionally. Okay. It's like you would rather have an A plus, but you're willing to settle for an A. You're happy with an A. It's still an A. It's still a great grade, but you would rather have just gotten an A plus, right? Or maybe an A and an A minus, right? You're willing to settle for an A minus, but you're not excited about it. That's conditional convergence. It still gets the job done, but it's not as strong a convergence as absolute convergence. So let's try a series and you'll see what I'm talking about. So we know this series, 1 over n, definitely diverges. It's a harmonic series. But if I do negative 1 to the n plus 1, now I have a couple of options. First, I need to test absolute convergence. So I'm going to take the absolute value, see if that series converges. So does 1 over n converge? It does not. Why did I make a sound effect? That's horrible. This diverges. So this series does not converge absolutely. So we took the derivative, or the absolute value. Now that series does not converge. So I'm going to move on to conditional convergence. Does it meet these two criteria? Is each time, so I'm going to ignore the -1. So is an greater than or equal to an plus 1? Well, yeah, if I have a fraction, and then I have a fraction with a bigger number on the bottom, it's obviously going to be smaller. So we meet that test. Is the limit as an approaches infinity 0? Yes. So I can say that the series converges conditionally. So you have to show those two tests. You should also show that you tested absolute convergence first, and then you're good. Okay, let's try another one. See if we can fit it into this small space here. Just like many of you do on your exams. Like you run out of space and you're like, well, make it fit. All right, let's try this guy right here. So we have the sum of n equals 1 to infinity of -1 to the n minus 1 n to the 1/3. -1 to the n minus 1, pretty much the same as if we start with 0 and do n plus 1. It really doesn't matter. Okay, so we have that alternating going. First, I'm going to test for the divergence theorem, right? So does this diverge? Well, I don't know because those negatives and positives, very confusing. So I'm not sure. But on this term, the cubed root of n, that's going to approach infinity. So you have positive, negative, positive, negative. It's a little iffy. So I'm going to start by taking the absolute value. Do we like that? Yep. So if I take the absolute value of this diverges because n to the 1/3, that sum goes to infinity. So we do not converge absolutely. Now I'm going to test these two conditions. Condition number 1, if the n term, I'm going to write the cubed root because it makes a little bit more sense to me, is greater than or equal to this guy. So if I add 1 and take the cubed root, is this smaller than that one? Absolutely not. In fact, it also fails the other test where if you take this of the cubed root of n, that equals infinity. So it fails all of the tests. So this does not converge conditionally, and it does not converge absolutely. When we look at the divergence theorem, it still says it diverges. So we're going to say that this diverges. Why? By divergence theorem. Okay, so you've seen an example of when it works. You've seen an example of when it doesn't. And that, my friends, is problem set 138.